So on Tuesday, we talked about classification and we listed a bunch of different classification techniques. And today, I want to go into a little bit more detail about the features for those classification techniques and talk about the best ways to actually represent them. Lots of people like to talk about end-to-end. They like to say you shouldn't actually come up with features, but even the people who are doing end-to-end are actually choosing the features that they're going to give to the system, though the features may be the string of words or the string of characters that they're actually going to deal with. So what I'm going to do is I'm going to talk about all the different ways that you should consider in trying to present your information to your machine learning technique from a natural language point of view. And I'll also talk about word embedding techniques, though again, there's still going to be a later exciting lecture where we're going to go into detail about how we actually derive embeddings. And no, we don't just train forever. There's actually principled ways of training forever in order to be able to get the results. Okay. What are the features? So we are going to try to do something like, well, the running example that I've been using is a bunch of newspaper articles, and you've got to sort them into 5 categories of news, sports, politics, something and something. You'll notice that I change the name of these things every time I talk about them because it's not very important what they actually are. So what we're going to have is some list of features that are going to be derived from some NLP form, some NLP bunch of text, and we're going to try to match them to some form of category. Now that category is going to be a relatively small, finite, discrete number of classes, like what language is it? Maybe part of speech tags, so we're going to do actually per word. Maybe movie genre, so we want to know whether it's a comedy, whether it's an action, and maybe whether it's an action comedy. The features that are going to be passed into this in almost all machine learning techniques have to be represented as a bunch of real numbers. And that is always something that people don't really tell you about until you start doing, and then it's just normal and you get completely used to it. All samples are going to have a bunch of features and a category, and the number of features that I have has to be exactly the same. You can pad things with zeros, but you want to put zeros in the ones that don't have any value. But each sample is going to be the same width. Okay, that vector has to be exactly the same. And in almost all machine learning techniques, these have to be real numbers. Now, it's okay because we know that integers are also real numbers, so we can do that. But importantly, they cannot be symbolic, okay? So they can't be part of speech tags. They can't be words. We have to convert these words into some sort of numeric feature representation, okay? And I'm going to talk about a number of ways of doing that and the advantages and disadvantages of all of these different forms. There is one particular machine learning technique that actually doesn't require that, and that's classification and regression trees. Though often they do, and almost always they internally convert them into numbers. But the way most classification and regression tree algorithms work, they can genuinely deal with a bunch of discrete values, typically not hundreds of thousands, but probably up to hundreds, and be able to build reasonable machine learning forms. But almost everything in the neural domain, in fact, I don't know anybody who doesn't do that in the neural domain, because there are relatively well-defined conversion techniques, which may not be absolutely ideal. And the ones you choose can be very important about whether something's actually going to work or not. So natural language doesn't have a finite number of words. Natural language documents don't have a fixed number of words in them. So every document is going to have a different number of words in it. So we can't just say, we'll take the first 100 words and just build our models on that, because sometimes there'll be 2,000 words and sometimes there'll be 12 words. And we'd like a way to be able to represent an unspecified, number of words in the document in a uniform width, so that we can then actually try to do our machine learning on it. And again, it doesn't matter what type of machine learning, naive Bayes, noisy channel, perceptrons, neural nets, doesn't matter. You've always got to get that representation as a number of, a fixed number of floating point numbers. So imagine we're doing something like reviews of movies. We've got some set of words and set of sentences. The movie reviews are not particularly long. They're not going to be as long as a novel. There will be a finite length, and it'll be relatively short. It'll probably be no more than a few hundred words. And then we have a class. Imagine it's some sort of very good, okay, bad, and very bad. They might have a number associated with them, a number of stars, okay, and they might just have names. For the output as well, we have to have numbers. We can't have symbols, so we're going to have to convert them. So no matter what the classes are named, we have to come up with numbers, okay? And so we could call them 1, 2, 3, 4, 5, okay? And that's fine. And we'll talk about sometimes when that's not ideal. Actually, no, we'll talk about now why that might not be ideal. Can anybody say why mapping the number of stars to an int from 1 to 5 might not be the right thing to do? So one of the things you have to be aware of when you're thinking about mapping something to a class, if you're going to do it through a range of numbers, these numbers have to mean something to each other, and the distance between these numbers sort of has to mean something. Now, it might be that 1 is worse than 5 and 4 is worse than 5, but is the distance between 4 and 5 the same as twice the distance, the double distance, when you have 3 to 5? And that might not be true for reviews, because typically most people who write reviews either write a 1 or a 5, or they're polite and they write a 4 or a 2, and only people who don't care write the 3. Well, maybe if they write a good review about how mediocre the movie is, they can validly have a 3, but maybe not. And some people will use a 3 to basically mean this is the worst movie I've ever seen, but they did choose to go and see it, so they don't want to admit it really is the worst movie that exists. So then that number range, 1 to 5, may not be a range, and they may just be discrete classes. It depends on the task that you're doing, okay? And so you have to actually think about that when you're choosing what the representation is going to be. And likewise, when you're choosing what the loss function is going to be, or the error function that you're going to calculate afterwards. So if we have a finite number of words, what we could do is we could just say, well, just take the first 100. But actually, if you're doing reviews, or maybe the first 500, and that'll cover almost everything. But the point is that actually the words at the end, typically the last sentence of a review is sort of a review of the review, and it's actually usually got a lot of important information in it. So if you're really wanting to cut it down, you maybe want the first 50 words and the last 50 words, or something like that. Or you need another representation for all of the words, okay? And we would like to get a representation for all of the words in such a way that we could sort of can use those words in our classifier if they've got any discriminative qualities associated with them. So the sort of things we could do is we could look at the number of words. Bad reviews are short, good reviews are long. Actually, probably extreme reviews, really bad ones and really good ones are long. The middle ones are probably shorter. But number of words is actually quite an interesting number. It's typically, it would be useful to have. Number of sentences actually probably tells you quite a lot. If there's lots of sentences and a few words, it means the sentences are short. If there's only a few sentences and lots of words, it means the sentences are long. That probably means that they're more in depth or something. And so that probably is correlated with something to do with the number of stars. We could also count the number of exclamation points, and the number of exclamation points probably is highly correlated with, again, things that are really good and things that are really bad, and nobody puts them in the middle. This is the most mediocre film I've ever seen. Exclamation point, exclamation point, exclamation point. I should do that next. But I don't think you're going to find something like that. It's going to be awesome with lots of, or awful with lots of exclamation points, and that probably tells you something. What you can also do is you can actually get a representation of the actual words that are in there, but you can't do them left to right because you don't know the length, and you're going to end up with a finite length. So what you could do is just say, does a word appear? So you could say, does the word good appear? Okay, or the word bad appear? And that actually helps. So if you know the important, interesting words and you actually find out whether they appear or not appear, that is actually probably going to tell you a lot of information. Now, what happens if the person says not good, exclamation point, and then gives us a 1? It's got the word good in it, so it must be good, but it's not really. And so actually the context of the word could make a difference as well. That's in the nature of language. We don't just deal with isolated words, especially in longer text. Actually, maybe tweets you could get by with it, because grammar is a little bit less important in very short sentences. But the negative form is actually quite important. And it may come after, it may come before, it may not be immediately before or immediately after, but that could be important. But remember that not good means something different from not bad. Not bad actually means it's a little bit good. Well, not good really means it's bad. So a movie that's not good is probably worse than a movie that's not bad, probably. But there's also something to do with expectations in there, but that's sort of hard to get into. Instead of representing the class that we are predicting, or the class of maybe the information that we're trying to pass in by a range, 1 to 5, number of stars, there's another very standard way of representing things. If there's a finite number of different words that could appear there, and these words do not have any obvious distance metric between them or ordering, okay, then you can represent the list of words as a vector. It would be a subvector in the overall vector, but a vector of a bunch of zeros and ones. So you could represent, if one of the subjects is business, you could represent as 1, 0, 0. You could represent sports as 0, 1, 0. You could represent entertainment as 0, 0, 1. If there was 5 things, then you would have 2 more zeros at the end of these, and then something like finance would be 0, 0, 0, 1, 0. Okay. This is often called one-hot vectors, and we use them a lot. In fact, many things that we use that are building data sets for machine learning will allow you to build one-hot representations automatically from classes. If you say, here I have this, whatever this feature is, you know, for all of the potential values in it, please just replace it with an n-sized subarray with zeros and ones for the appropriate form. You want to do that when there is no immediately obvious relationship between the classes that you're actually trying to encode, and no ordering between them, and no obvious distance metric that put them on some linear list, okay? So if you wanted to represent the classes for business, sports, and entertainment as 1, 2, 3, that would sort of be bad, because it would be saying that entertainment, okay, is more than twice the distance away from what sports is from business. Now, I know you could come up with some argument that that would be true, but realistically, that's not what you want to do, okay? So the one-hot representation, when the things don't have any immediate relationship between them, and certainly have no ordering relationship between them, a one-hot representation for a categorical feature is a reasonable thing to do. How do you represent the words though? So we've maybe talked about the classes, we maybe talked about the occasional word like good and bad, and how do we represent all of the words, okay? And the answer is, for first approximation, we decide on a vocabulary size. It can be quite big. Maybe we don't want it to be millions, but you know, being multiple thousands or multiple tens of thousands is probably perfectly reasonable. And we one-hot the words. What we do is we have this big long array with all zeros in it, and position 347 represents Nebuchadnezzar, and if Nebuchadnezzar actually appears in the document, it goes from 0 to 1. Remember, when you're doing a vocabulary, you would also want to have an other, and the other is any word that appears in your actual textual documents that is not in your vocabulary will be represented by other, and you really want to do that. Lots of people think, oh, it doesn't really matter, but there's a lot of information in the things that are different. Okay, if all of a sudden you happen to have a document which is not even in English, almost everything will be 0, and you'd really like to know that other is there and everything is near 0. The isn't even 1, and that actually could be very valuable. So you always want to have big long list of vocabulary plus one more, which is anything else. You could set not just zeros and ones for any time an occurrence happen. You could actually have the number of occurrences of the word. Okay, and that's often a perfectly reasonable thing to do as well, especially maybe with the other, because you know there might be one word in every document that's never been seen before, but if other ends up getting a value of 4,000, that probably tells you something weird about the document that distinguishes it. And even though you've never seen anything like it before, it's different from the other documents. And that's a very useful thing for machine learning. The vocabulary you choose for that array should try to be as general as possible, so you don't have to update the vocabulary every time you get a new document. That wouldn't work because you'd have to retrain your model every time and regenerate all your training sets. You don't want to do that. You maybe want to update your vocabulary size every so often, or the choice of the words that you have in your vocabulary. That's a reasonable thing to do, to consider, but you want it sort of to be big enough that you don't have to do that every day, and maybe not even every month, but maybe once a year, depending on the task that you're actually doing. You could say, I'm not going to represent a high frequency words, a very high frequency words, words like the, and of, because that will take up space. And the answer is, it will take up space, but actually there's not very many really high frequency words. So it might save you space of 50, but it's going to save you space of 50 and 10,000. And so it sort of doesn't matter, okay? And actually there might be a few cases where if the does not appear, there's something weird going on, and that might be useful to identify how that document is different from everything else. You could say, I'm only going to do the content words, and that is also sort of something that's sometimes worth considering. And you can do that, or you can in fact have more elaborate ways of selecting that vocabulary. You could have a look at the vocabulary of some reasonable set of documents, and what you could do is you could choose the vocabulary based on how often they appear in some documents and do not appear in other documents. So imagine all your documents are about the European Parliament, okay? The word parliament is next to useless. It's going to appear in almost every document, even though it's a content word. It sort of tells you nothing at all, okay? While maybe there's another word that only appears in some documents and not in other. Brexit, although maybe that appears everywhere. Maybe that's just because I'm a Brit. I think it appears everywhere, sorry. Brexit appears only in a few documents. So Brexit is this really strong distinguishing word. And there are good ways to actually calculate how words actually may be good at distinguishing. There's a thing called TF-IDF that we'll talk about later that actually talks about doing that. So you could do some other more complex selection criteria for trying to find that vocabulary. And you could probably make it shorter, the array shorter, which could make training faster, and it could be not affect the results. In fact, it might even make the results a little bit more stable. You can also just represent all the words that appear more than once, but remember, unique words actually might give you a lot of information, or maybe you want to know the number of words that appear once and only once. So there are some choices there that you can have. the default form is often what's just called the bag of words, and you just take the vocabulary, take the most frequent ones, and you maybe look at the distribution to decide where you're going to stop. I've maybe mentioned this before, that if you look at a distribution of English of natural text, about 43% of the words will appear once and only once. It's a little worrying that it's 43. It's sometimes 45 and it's sometimes 40. But, you know, if it's nothing appears once, there's something weird. Probably there's duplicate documents in there, so there's a boost. And if you look at the lowest frequency and it says 20, that means you've probably got 20 copies of everything that is in the data set. We've actually done that analysis before. But you can choose something about that, and that can be perfectly reasonable, okay? Notice that a vector is mostly going to contain zeros. So if you've got 10,000 words in your vector, there's only a few hundred words in your actual review, so most of that vector are going to be zero. There's actually pretty good computer science data structure techniques. In fact, maybe you've even written them, ways of representing very large vectors and matrices that are mostly empty, and the so-called sparse arrays. Python has a whole bunch of wonderful ways to do it. And so actually you don't need to have, you know, a representation of 10,000 floating point numbers in order to be able to represent bits 0 and 1. You can actually get pretty good representations of that, but still you have to iterate through them, and that just takes time. Oh, it's a 0, it's a 0, it's a 0, so you don't have to do anything, but you have to look to see that it's a 0. As I say, this is what's called a bag of words, and it's called a bag of words because what we do is we take all the words that are in the review, and we cut up the paper into individual words, if you're old enough to know what paper is, and take these words and put them in a bag and shake them. We now don't know the order of the words anymore. So we don't know if that word not came before the word good or came before the word bad. Good and bad could be in that. We've lost that information, okay? And that might still be okay, and it's a way to simplify the problem, but there is a piece of information that's gone when you actually just put them in the bag and shake them. It's not a real bag. Also, if we do that, we maybe don't even care about the occurrence of words. So if you just put the word in the, if we've not got it in the bag already, that it would be hard to do that because you have to look inside the bag and see it's there. But you could sort the words, find out what the occurrences are, and only take one and keep them in the bag. But what's deeply important about all of this that makes machine learning actually work is we can end up with a fixed width vector that represents the words in the review no matter how long the review is. It's worth talking about another technique at this point that's different, and you might think about it, and we do sometimes use it, especially in neural techniques, but it's a little different and the consequences are a little different, and it's only really going to work in a neural form. What you could actually say is you could look at the longest review, or maybe the almost longest review, and you find an upper limit that maybe gets at least 80% of all the words that are there, and just say, I'm going to represent up to 500 words in every review. If it's shorter than 500, I'm going to put just zeros in to fill in the space. And then what I'm going to do for each space before that, I'm going to have an integer that represents the word. You can do that. And in some neural forms, in the way the data is treated, especially if the data is treated as a sequence, that can work. If you're just going to put it in as a flat vector into a feed-forward network, into a Bayesian form, it doesn't really work very well. Because then your machine has got to learn that the word good in position 17 means it's good. And if the good's in 23, it's also good. And if the good is in 134, it's also good. And now you get a new example where the good is in position 87. It's never seen good in the position 87 before. So it can't learn that that is a good review rather than a bad review. Now, as with all machine learning, actually, machine learning techniques become very similar if you have an infinite amount of data, a perfect learning algorithm. But we almost certainly never do. I wonder what went wrong there. I'm now in the dark so that I can look like a real wizard. There we go. There we go. There we go. Okay, sorry, I wasn't doing that for dramatic effect about how bad that technique is. Oh, wait, I could do that now. I'm not going to do that. We could use a representation that just looks at the first n words. We pad everything up to 500. And if we've got a particular training algorithm that can deal with that, well, that's a good thing to do. But I think the approximate thing is it's got to be able to deal with sequences of words before that's going to work. So if you're doing Bayesian, if you're doing classification regression tree, feed forward neural networks, no matter how complex, that's really, really, really not going to work. So you should not do that. And you should think about the bag of word type representation to do that. Reviews that are similar, i.e. got the same number of stars, these vectors with all the zeros and ones in should be similar. That's really what we're saying. It's not quite what we're saying because we're going to put weights on these different things and then try and train it. But that's actually what we're saying. What we're really saying is, given that big array with all these features, especially if we're doing with simple zeros and ones, we don't have to worry about the weighting. And we've got another one with zeros and ones. The ones that are most similar should have the most similar number of stars. Okay? And that should be the case. And we should find something a representation which actually does that, because that's sort of what we're saying when we're giving this vector for sample 1, this vector for sample 2, this vector for sample 3. We could just take a simple difference. We could take an edit difference between them, and the things that are closer. We could, especially if we're doing some sort of number of occurrences, we could do some sort of cosine similarity. That sort of works too. But it's important to note that we're taking all words, all different words being equally separate. So if the review said, I love the film, 5 stars, and another review said, I hate the film, 1 star, and somebody else said, I like the film, 4 stars, okay? The distance between I hate the film in this vector space and I love the film in this vector space is, depending on what you're ever doing, there's only one bit different, or one vector that's different, which is the representation of the word love versus hate, and then versus like. And we've effectively got all of these words being equally different, okay? And that's sort of not right, because love and like are in some sense closer together. They're definitely all on the positive side, and hate is down there on the negative side. And although there'll only be rarely cases that are as explicit as this, this certainly happens where some words are closest to others and some are not. And we want to take this into account. We probably don't really care about the function words. We really care more about the content words, but we'd like to have a better representation that could more reasonably learn that love and like are relatively close to each other, while hate is definitely different in the spectrum, so that when we're taking these distance metrics, it would be a more reasonable thing to do. We don't need to have just a binary representation. Maybe we could get another representation that could tell us something about the distance between words. So imagine that we've got an integer that represents 1 to 10,000 for each of the words that we actually have. We could have an array, a big matrix that tells us the guess difference between one word to any other word. I'm not going to say how you get that distance, because we could sit here and, we could set it as a homework, and we'll give you 100 words and you have to tell us what the distance between them is. And you'll discover that that's pretty easy for things like love and hate. But I want you to tell me the distance between chair and snake, okay? And is that further away or closer than table and puppy, okay? You can put that in the chat and tell me what number you think it is. I know somebody's already looking it up as a word embedding and then getting the difference, and you're going to stuff in 300 floating point numbers into it. I get the joke. That's good, but don't do that, please. So you could get a distance metric, or you could maybe have classes of words that actually could get distance metrics between them, or you could try to cluster the similar words in some way. Like we often talk about that, but there's an awful lot of way to cluster things. But all of these things are worthwhile, and we're actually going to go on to talk about ways to try to address that so that love, hate, and like don't have effectively an equal distance. They've got an appropriate distance for the form. Although be aware that we're going to multiply the number of representations and have even bigger numbers, and you thought that an array of 10,000 was big, you know, we're going to have things a lot bigger than that. And remember, we are ignoring the contextual information here. So even if we have love, hate, and like, and have a nice representation, we have a distance metric that actually tells us when these things are close or not. We're not really caring about the words at either side. Now, the bag of words thing is pretty good, okay, because it makes everything the same length. And what we could do is we could actually say, well, we're not just going to have a bag of words, we could have a bag of bigrams, okay? And that works pretty well, but we now have 10,000 words and we've got bigrams, so we've got 10,000 times 10,000, okay? And very quickly you're having to call up Amazon and get them to send you more memory because you've used it all up. Even if you've got really good representations of sparse arrays, that fills up very, very quickly. But maybe you could select the most useful bigrams and represent that. And we often do things like that. And there are techniques to try to find the most useful, the most discriminative bigrams, okay? I've already talked about that. All right, so they treat these as the same. Now, word embeddings, which I'm sure at least you've heard of the term, we're going to actually try to define it in future lecture, but word embeddings are saying, I would like a representation of the word that tells me something about the meaning of the word. And I use the word meaning in the lightest possible sense, okay? Because it's really, really, really hard to come up with something that genuinely captures the meanings in all contexts. That is almost impossible. Word embeddings are usually pretty surface oriented. What they actually end up doing in almost all the ways we train them, even in the most current elaborate ways, are looking at things with respect to co-occurrence of the word. So we're looking at words round about the word love, hate, like. We're looking at all the words round about it and trying to find out if words are similar, if they've got a similar context. And that's not the same as meaning, okay? But it's definitely way better than just having like being representing 376, love being 487, and hate being 2. It's not, that doesn't mean anything at all. I talked about getting that matrix that actually did word to word and gave you a distance, okay? And that's a one dimensional distance metric. But imagine we had multi dimensions to that and we could actually get a representation of that. And that is something we'd like to be able to do. And that's what word embeddings actually are. They're often referred to as being dense representations. The sparse representations are the ones that have got all the zeros and occasional 1 in them, while the dense representations are mostly got random floating point numbers in them. Now, although they're technically not random, in almost all word embedding forms that you get, they're effectively random. If you plot them, they're noise. If you look at them, they're noise. Which vector represents which bit of information is noise. It might be that a vector does actually correlate strongly with something like geoposition of the information that's actually there. It can't do that, but finding it is next to impossible. And every time you train these embeddings, it could randomly move. no, they are effectively random, at least for you understanding the content of them. We can do things with them that help us and could actually then predict correlations between things, but we don't know what these representations actually are. And it's okay that that's the case, because what happens is we can use them and they work. Remember, one of the key things that David and me have been saying to you, that we're talking about all of these different ways of doing natural language processing. And when you want to know which way is best, the answer really is the one that works best for you. Actually, maybe not for you, but for the application that you're actually dealing with. And there could be other things about, I want to use word vectors because word vectors are great, but actually you're working in a language that doesn't have word vectors. Okay, you could train your own, but there are issues there. Or you want part speech tags because that's the best thing that you actually want to do, but you don't have part speech tags in the language you're dealing with. Or the domain you're working in is not the same as normal English, it's Twitter or something like that, and then things don't work. And so there may be various conditions that there might not be one straight answer about what's actually best. People argue about whether word embeddings, a big bunch of floating point numbers, actually mean things or not. And the answer is they're not meaningless. It's very, very clear that they actually have interesting properties, but discovering those properties is a research problem in itself. And although we have done a number of things to try to work out, does it represent style of the document that the thing actually comes in or not? The answer is it sort of does, although they're quite surfacey in the sense that they're very, very word, but word and synonym and sometimes antonym representative. So in other words, if you take a story like Romeo and Juliet and a movie like West Side Story from 1962, but you've probably at least heard of West Side Story, okay? And get the representation of the play and try to get a distance metric in word embedding space, you won't get anything useful out of that, even though they're the same story. They're fundamentally the same story. Basically, two rival families that hate each other and want to kill each other, and there's a boy and a girl who fall in love, and it all ends tragically. Wait, am I spoiling that for you? I'm sorry. If you don't know the end of Romeo and Juliet, you should go and read it, or West Side Story, because it's got better music in it. So most of these embedding things are really towards the words, but they actually do pick up the information, like the distance between like and love and hate. Okay. Right. Word embeddings. So word embeddings are the new fashionable way for us to be able to take typically a pre-existing set of data and go and train a lookup library for words to a bunch of random floating point numbers. They're not random, but they look like random, but they have certain properties that we'd actually like to do. People worked on this for some time, but really the time in NLP where people started using big embeddings was really Google Mikolov in 2011 or 12 introduced this idea of word2vec. Again, there's a whole lecture on word embedding later. We'll talk about the history and we'll talk about the interesting things. He came up with this. He also found that, you know, animals were closer together in this space, and capital cities were closer together. He also found that there were some funny properties that if you had a representation of king and you subtracted the representation of female for it, from it, okay, you actually got something that was representation of male from it, and added the representation of female, you got something that was close to queen. And actually in the original paper, he talks about this and says, you know, but this can't really be meaning. And the answer is it isn't really meaning. There's just some dimensional properties that are actually there. And in fact, theoretically, all of them are there. Then some of them are easier to get than others, because there's a lot of dimensions in here. The width of these things is pretty wide, but even then there can be other things encoded in there. So I wouldn't take too much from that. okay? Glove, okay? Glove was often shown to be better. It's a word embedding representation, and no neural networks were harmed in the process of building Glove. Glove is actually built analytically from data. It's computationally quite expensive to do, okay? You need lots of memory to do, but once you have it, you get this thing, which in those are almost all 300 floating point numbers wide. For Word2Vec, Glove, and Skipgram, which if you want to train your own, a single word has got one representation. So you end up with a big lexicon, okay, which you can download or you can actually use online, and Python will just look it up for you on the fly if you're online and be able to get these vectors, and it can be very useful because it's quite big to download. You don't really necessarily want to do that. But you get the same representation for a word no matter what context it's in. But people were aware that, you know, the word apple means something different when you're talking about fruit, or if you're talking about a computer, or if you're talking about a computer company. Yeah, Apple Computer and Apple Computers, as in ink, is different. And so the question then became, can we actually get a representation of a particular word that's dependent on the context that it's in? Okay, so we already discovered that some notion of bigram actually helps. And the point is that if we could get a Word2Vec, a word vector representation, which can take into account what the representation of the words are round about it, we no longer get a single representation of good, we get a representation of good within the context that it actually appeared in, maybe with the word not in front of it, or maybe with the word not some distance away, okay? Sorry, can't think. Oh yeah, not bloody good. Sorry, I thought of another one there, but not bloody good. I like living in America. I'm allowed to use the word bloody, and people think it's a very light swear word. It's not a really light swear word where I come from. But anyway, I can use the word not bloody good. So it's a little bit further away. We get a representation of that good that could take into account where the word not is. This is what's called contextualized word embeddings. They're quite hard to train. Elmo was one of the first ones to do it, and it was followed at the end of 2018 by something called BERT. When we talk a little bit more about BERT, you've probably heard about BERT already. And we're not just talking about the character on Sesame Street, but they are named after the characters in Sesame Street. And BERT is best described as wonderful, but I'll come back to that. These pre-trained models are great, okay? If you can use them, and you can't always use them because there can be other constraints or they might be not the best thing, you can train your own. But to get really good word vectors, you need a lot of data, you need a lot of context, so it gets to see things in a lot of context, especially contextualized things. You need an awful lot of data. You probably can't download that on your laptop. We probably can't make you do that in homework in a week because you won't have enough time to be able to train the model. In fact, you probably wouldn't have enough time to download the data that you need to train the model. So that's not really practical. But you can train your own Word2Vec with a thing called Skipgram. And basically what it does, it's of course not contextual, it's just looking at particular words, but it is caring about, in general, the words that appear round about them. And that works very well. In fact, that works really very well when you have a reasonable amount of data. So we're probably talking at least 10,000 words. I mean, don't know what the limit is, but also if your domain has can be modeled like that. I know that's sort of cheating because I say it's good if it's good, because it is good if it's good, but it can work incredibly well. In fact, a well-trained in-domain word embedding for your domain will always be better than the pre-trained model, always, okay? But only if you have enough data for your own domain, and only if your domain doesn't really rely on the external world, and that's relatively rare. But sometimes you're in a position where things are so specialized that it's really sufficient, and so you might find that air traffic control, actually you can train your own forms and it's just fine because it's got a relatively limited vocabulary and a fairly fixed grammar. And when it doesn't, nothing's going to get it right. Okay, it's just too hard because something's gone majorly wrong. Actually, most of the time something's gone majorly funny rather than a plane's about to crash. But, you know, once it goes outside its standard form, it sort of doesn't work, and almost nothing works because it's a really weird condition. But maybe, you know, dialogue in a game engine might actually be something that's very specific because it's got a very specific meaning of maybe even standard words, but got different meanings about them. And so that might actually work. So you have to ask this question, is the data that you're working on generalized natural language English or whatever language you're dealing with? Because if it is, then pre-trained word embeddings are really good things to include in whatever downstream machine learning you're doing, be that naive Bayes, be that CART, be that a noisy channel, or any form of the neural forms. Any of those are perfectly reasonable. But, you know, if your data is like others, pre-trained models are going to help. Okay, because they trained on more data. They don't know about your problem, but if your problem has data that would be a reasonable subset of the data that they might have trained from, which is every newspaper article, every version of Wikipedia, every version of a book published, notice that all of these things are typically well-edited text, okay? So they're not social media text. And so these things are often not as good on social media, although there are now versions of these things that do work on social media type text, i.e. spelling errors. Next thing is, do you have enough examples? And the question always is, how many do you need? And the answer is, you don't have enough, okay? Because it will always be better with more, which is not a useful answer. But really, you've got to have thousands of words, tens of thousands, millions is better. If you've got 100 million, you're probably going to be pretty safe. And if you've got 1 billion, yeah, that'll probably work. In fact, once you start getting above 1 billion, you might actually consider the contextualized ones. That actually might work. The other thing is, are there special meanings for words within your domain? So are there standard words, but they mean something very specific in your domain? Almost all task-oriented dialogue systems are like that. They've got really specific meanings for things because people are trying to achieve a task, okay? And for example, if you want to ask the time for the next bus to Squirrel Hill from CMU, and so you ask the system and it's using a word embedding thing, and the point here is that Squirrel Hill is actually really important. It's not about squirrels, it's not about hills, in spite of you have to cycle up that hill every day, but it's not really about hills. And so you don't really want it to go and find a bus that goes to Badger Mount instead, okay? Because that's an animal, and it's sort of an animal that might be around the place, and you know, some type of hill, a mount. That's not what you want. You actually want Squirrel Hill. You don't want something else that looks like Squirrel Hill, okay? You want something that is Squirrel Hill, and therefore you want to be a little careful about these things when you're dealing with pre-trained models. Do you have these special meanings, okay? And you really should test it, is the answer, to ensure these are different. How wide should your dense vector be? Well, you had 10,000 with your, or more, with your sparse one, so anything smaller is probably going to be better. There is no fixed answer for this in any way whatsoever. There's no good way to even experiment because it's just too expensive. Training one of these really big models can take weeks on data, and then you have a whole bunch of downstream tasks to try to find out whether it's better, worse, different. Okay, so you're not going to say, okay, I'll try all the numbers from 500 to 1024 and see whether which one's best. And each time you train, you almost always have random starts, it's probably going to be a different number. In the non-contextual one, they're often 300. And I'm pretty sure the reason that they're 300 is there was some programmer who started off doing this going, I don't know, 300. And they typed in a random number and they stuck with it. They maybe did 100, 300, and 1,000, and the 1,000 ran out of memory, and the 100 they ran 4 times, and they got random results, and then they ran the 300, and it was better, so they just went with the 300. But nobody really tested whether 500 with that training technique and that particular data set was good or bad. Sometimes you can reduce them, and you can actually train things to reduce them and get smaller, because 300 is still quite a lot. And also remember, multiplying a random floating point number with another random floating point number is much more expensive than multiplying any floating point number with 0. Okay, almost all hardware multiplies by 0 much faster than any other number. So it's not just the size, there's some other complex forms. The contextualized ones are often bigger. I don't know if that's because they want to show off or it is actually better. BERT standard 768, but there's a large version which I think is 2K, but I actually can't remember. I think it's 2K. And this is already getting pretty big, okay? Although there's other things that are about BERT. BERT really gives you a representation for the sentence rather than the individual words. So what you do is you give it a whole sentence because you need to give it the context in order to be able to get, and then you'll get a list of word embeddings back, and then you can do something with them, which I'll talk about in a minute. We don't really know the answer to that. And actually, if you look at the number of parameters that you're actually talking about, these are really, really big. I mean, you don't want to make it as dense as possible, because then the machine learning won't be able to benefit from easy techniques to be able to separate things. You'd like it to sort of spread the numbers across different parts of the vector so that you could deal with the size of the object, or whether it's animate or not, or things. You hope it would get things like that in different places, because that would be very useful. And maybe you could put them all down, but think of the size of the number of different numbers you can have with 768 different floating point numbers. Okay, so that's 2 billion different possible floating point numbers, because it's the same representation as it's not 2 billion, it's bigger than that. The number of possible ints you could have, because that's the number of possible floats, although they're over a bigger space, to the power 768. Okay, that's more than there are seconds in the universe. That's more than there might even be atoms in the universe. So there's an awful lot of different things. You could represent any state in the universe by that. Maybe not the universe, but at least in southwestern Pennsylvania, you could represent that. So we don't really know, but it's an interesting question, and it would be nice if we could find something that was better for that in some way. Okay. Oh yes, right. So we don't know what length they should be, and we also don't know what features mean. So we don't know what particular coefficients within the vector mean. We have no information. That we could look for some sort of correlation. There's no guarantee any one correlates with anything that's useful or understandable for us. There are correlations, we're fairly sure about that, and we can try to predict correlations or predict values that are correlated, and it works pretty well, but usually through some neural net to do that. So there's some nonlinear transform in order to be able to do that. Very rare it would be a simple linear transform, but it often happens, and you can actually get something out of it. So we can't know what the coefficients mean, but we can still have some control over the vectors. We can sort of just say, well, I don't know, it's just 768 numbers. What we can do is we can say, well, here's the 768 numbers that represents the word that comes from BERT. But we could concatenate on the end of that other explicit pieces of information that we do know what they represent. And so what we could do is have a representation for the word, and then we can have a representation for the part of speech of that word. Now, there's probably information in the 768 that's like part of speech, probably, but we don't actually know what it is. And for any machine learning thing to try to work out what that distribution actually is, it's probably going to need at least the same amount of data as what you got for training a part-of-speech tagger, okay? And in your data set, you might not have that. So it can be worthwhile running a part-of-speech tagger on your data, getting the part-of-speech tags out of it, and then representing the part-of-speech tag and concatenating that to 768 points. And so you've just got maybe a one-hot representation of a sparse representation of the part-of-speech tags. And remember, one of the reasons we're doing part-of-speech tags is because we would like to reduce the dimensionality of our representations and make it easier to be able to train and predict things, because we don't need all examples of all words in all contexts, because the part-of-speech tag has reduced the occurrence of these things to a smaller number, and therefore we get to see patterns easier. And in that same way, even though there may, in fact, there almost certainly is some part-of-speech type information that's being encoded in the word vector, there probably is not a good way to get it out unless you have a lot of data or a lot of training or a complex model. So why do you want to do all that when you have that information trivially and you can just put it in? Might not be exactly the same, but it's probably going to cover the same thing. In the same way, you could start concatenating other known pieces of information there. And even though the number of bits of information that you're putting in there is less than what you have for your word vector, that's okay. Most machine learning and all machine learning things are going to look where what's the most discriminatory features and find out, oh, part-of-speech tag actually helps me a lot. I get the answer in one layer rather than have to do 17 layers or something by using the part-of-speech. In the same way that we could do part-of-speech, dependency parser parent, other information that's in there, if it's a number, if it's got capital letters, other features can actually work. And therefore we can control in our representation for a word what the information is, not by necessarily taking it from the word vector, but by concatenating other pieces of information in there. And we will often do that. Word2Vec and GloVe are pretty standard, and definitely for relatively targeted things, they actually work pretty well. It's always a little embarrassing how well they work, but there's this little statement that came out in, I'm not the only person who says this, it came out in at the end of 2019, and that is everything is better with BERT. BERT is this contextualized word embedding using transformers. It was released on arXiv in November 2019. It had more citations by the end of November, and rather interestingly, it was released about a week before one of the major deadlines for the conferences, one EMNLP, I think it was. And about a quarter of the papers at EMNLP actually used BERT. Now, admittedly, we already had a thing called Elmo that was sort of similar, so you could easily swap out Elmo and put in BERT, and BERT was better, done by Google, and it actually gave substantial improvement, state of the art, on 11 standard NLP tasks. And almost nobody had done at that time saying, okay, here's a standard representation, I'm going to try it on all these tasks. They would typically get a new representation and try one or maybe two tasks. But what Google did was they said, well, here's 11 tasks, now called Glue. And we actually get, better than anybody else has ever got on these 11 tasks. It's one of the most referenced paper in the last 2 years. The reason it's got a 19, even though it came out in 18, because it was actually published at NAACL the following year, because it was submitted as a paper, and they have blind review in that conference. I did not review it. I would not be appropriate to review it. But I'm sure the person reading it would know exactly who the authors are, because if they were reviewing it, they would have already used BERT and read the paper on arXiv from 6 months before. It wasn't 6 months, but 4 months before. BERT made a big improvement in almost everything in natural language processing. It actually made word embeddings not just a standard, which I think they were before. It actually said this is the best way to do it. Since BERT has come out, there's been a whole bunch of better things. In fact, if you read the BERT paper ever, they actually explicitly say, this is what we're trying to do. This is really computationally expensive. It's going to cost us a lot to run this multiple times to find out what the best hyperparameters are. So we're going to do it once. We're going to try and make the best guess of what we think something might be and see whether it works. And it worked really well. And so they went with that. But they admit that you can probably do better if you take a little bit more care on how you train, what the size of your particular forms, and et cetera, et cetera. So there's a whole bunch of that. And so since then, a whole bunch of people are training to do more, and there's a lot better and certainly more robust things than BERT. BERT's pretty good, but it can sometimes flake out at the edges if you're using things that are not really in the domain of what it's actually dealing with. But there's a whole bunch of things, almost always with the word BERT in them. So Roberta, Albert, exist that have different forms. There's also multilingual ones that started off only in English. People trained in other major languages, and then they also trained cross-lingually, and that actually helped. There's a CMU one, which is better, and it actually doesn't just train on more data or different data. It actually does a different representation of how it does its training. One way of looking at it is one of the things that BERT is doing is it looks at the sequence of words. It randomly deletes words and tries to see if it can predict the words that's there, and it uses that information to try to update its transformer and attention. One of the things that XLNet does is instead of just deleting one, what it does is it tries to randomize the order of the things round about. So it actually has a much better prediction for things that it's never seen before, because it's not just depending on the standard sequence. It actually can pick things up when it's never, it can predict better for sequences it's never seen before. And XLNet also beats, I think it only beats 10, I can't actually remember that, of the NLP tasks, and it's also better. It's computationally huge as well and bigger, and it's not available for every language yet, but I might be wrong about that. I might be out of date. It was a CMU student who graduated last year who did XLNet. Okay, so we now have representations for words, but remember way back at the beginning of this, if you do remember way back at the beginning of this, I said we're not looking at strings of words and trying to represent them. So if I said you take the first 500 words, we now have 500 by 768 to do our representations, which is bigger than 10,000. Yes, it's bigger than 10,000. What do we do with all of these representations of the words? Well, we could add them up. That's somewhat silly, but it works surprisingly well. It works way better than what you think it should. You could average them, effectively normalize them so they don't get too big. Although some of them can be negative, they don't have to be all positive. You could take the max, often called max pooling. That also works way better than what you'd expect. If you imagine that you have this big long vector, if you imagine that the dimensions in the 768 space that you've just projected your words, what you're doing if you're taking the max is you're taking all the words and joining them together and finding out effectively what's the most unique distance, or not distance, dimensional vector in the true sense of the word vector, so it's got a direction that your group of words represents. And so that's what max does. And that works, okay? It's not just a weird idea that happens to work, it's got a theoretical underpinning, and it's relatively easy to do. Other things you can do is you can take these representations and you could actually try to learn an embedding for all of them together. And actually with BERT, you get one. So you actually get one at the end. And you can use that, and it's usually pretty good, okay? But if you get a chance to actually not just use it fixed and actually use it and fine tune it to your particular form. So you take that as an initialized form, and this would only reasonably work in neural net training. It's pretty standard in neural net training, where you take the first representation that you get from BERT and then you change the model for each document, and therefore your prediction, you can do pretty well on this. Okay, remember there are an awful lot of words, and some of these words could be collapsed, and you don't really need to care about them. I'm male, so there's only like 4, maybe 5 different colors, and so all these colors like peach and coral and orange, maybe that one's different. You could group them together, but realistically, you could group them together. I mean, unless you were really caring about particular colors, but most of the time you could put those together, and so you could try to reduce things. Word embeddings actually allow us to do this, so we end up with a distance metric where in that space, words which have got less distinction between each other are closer together, and words that are very different are spread apart. We could also care a little bit about joining the representations of the previous and the next, though most of the word embedding sort of has that, but definitely the additional information like part of speech is sort of a good thing to do. Part of speech allows you to reduce the number of words. Part of speech allows you to look for patterns which are abstract grammatical patterns rather than word patterns, bigram type patterns, and therefore this makes it easier to learn. And there's maybe 45 different tags or 10 tags if you use the universal Google tag set, which loses some information but is easier to label and is available in more, but 10. So you end up with smaller representation, and so your machine learning can find patterns that are more important. Instead of saying things like this word actually means good if it's preceded by a determiner, but if puts any adjective in there, it actually makes it worse. Okay, and that would be a useful thing to learn. But imagine if you had to learn that rule from words, you then have to say not that it was preceded by an adjective, you'd have to say it's preceded by, well, list all the adjectives, and you have to have all of those contexts. So, but if you had it in the part of speech space, maybe you could do it. And maybe you could get that in the word embedding space, but it would be harder and you would need to give more examples. So being able to reduce things to a smaller number of hopefully still meaningful information means that you can probably train things faster. And that's an important thing to always remember. And there's this thing about machine learning people and NLP people, and I'd like to point out that I'll often talk about them as 2 different groups, but they're really like this. There's not really a distinction. The NLP person is a machine learning person sometime, and a machine learning person is an NLP person sometime. In machine learning, in MLD, okay, what you're doing with machine learning algorithms is want to get the best possible result given the input data. That's your job. And it's not just that, because you want to also say what's easy to learn from the data, what's hard to learn from the data, how much data do you need, what's the distribution of the data that you need to actually do that. But you want the best result given the existing data. And believe me, I want that too. Okay, I want my machine learning algorithms to train the best given the data that I have. But when you're on the NLP side, that's not the only thing you want, because you want your application to be the best. You don't just want the machine learning to be the best. And you know that the machine learning can be better if you give it better features. If you give it more appropriate data, it can be better. So in other words, it's not just, I'm not going to touch the features and I'm going to let the machine learning actually work out how it is. I would like it to do that. And it does do that. And it does that in ways that are actually wonderful. Because doing that myself would be awful. But I'm going to add new features if it makes it better. I'm going to add more features that will make it easier to learn. And knowing what features you want to learn is sometimes called feature engineering. It's sometimes thought to be bad, but all real systems do it because ultimately the application you want to run better, and you're not just looking at the theoretical point. That's not to say that machine learning people should start looking at the features. No, they should be making sure that the machine learning algorithms are unquestionably the best and better than what they were before, because that will also make everything better. Okay, it's just 2 dimensions of looking at the problem. Okay. Too many features. So if you actually do too many features, things begin to break a little, because now you can actually find some context that allows you to predict the result and get absolutely no generalization from it. Because now what you could get is, oh, if I learn that feature 4,368 is minus 356,268, the answer is it's a business document. And I learned that because, well, there was one example in the training thing, and that number appeared there and nowhere else, and no other sample had that. So I've got 100% prediction based on that number. I know that I can get that right. And that's pretty useless. We're trying to get something that generalizes so that when we take things that it's never seen before, it can actually predict the right result. So if you give it too many features, it starts finding these patterns. This is sometimes called overtraining. And all systems will typically end up overtraining if you're not very careful. So how much is too many features? And that's sort of hard. You've got to make sure that you've got a held out test set. Actually, that's usually not right. You've got to make sure that you've got a held out validation set that you actually tune all your parameters on, and all your the length of them and the number of extra things. And once you've decided this is the best you can do, so you don't train on that validation set, but only use it to find out what your best model is, then you can do it on the test set. But actually you end up overtraining on the validation set. So you want validation set number 0 and then validation set number 1, and then you have actually the test set. And so you train and test and validate. And so you've got to be quite careful about this and make sure that you don't overtrain. Pre-training is really very good. This is like the language model, really. It's like if I can independently train information on other existing data for which I have a lot more data, I can help that for my particular targeted application. So remember when we were talking about the noisy channel, we separated things out into the prior, the language model, probability of the words, and we had the observations, so the probability of the observations given the word. We can make the probability of the observations actually deal with the particular data set that we have, but that prior, we can train from data. That's what pre-training is. And it is good if you've got the right data in your pre-trained model that matches the data that you're actually dealing with. So if you're dealing with Wikipedia, it's great, because actually Wikipedia type data is very good and often used in pre-training. The other thing is, it's often a very good idea to look at your system and see where its errors are, and then try to understand why it's doing stupid errors. And why it's doing stupid errors typically tells you what type of features it doesn't have. And this might be things like, yeah, I'm dealing with all this, and it always seems to get all the numeric values wrong. And then you realize it absolutely doesn't know that these tokens have got numeric values in it. It doesn't know that they're ints. And they're all different. There's a whole bunch of ints that keep appearing all over the place. But as far as the system is training, it's just like, there's another value, there's another token, and it doesn't know that these are similar to other numbers. And so maybe you want to do something to fix that, to actually get a different representation for numbers in your training so that it can see that they're the same. Okay. And so it's good to look at errors because it will often tell you things which are missing, and that might tell you the types of features that you should be adding to make it easier to do that. You can't always do that, but it's always deeply embarrassing when somebody else comes along, it's usually some old person with a beard, and comes in and says, you can do that, and you do that, and everything gets better. I like when I can do that, but it's quite hard to do that in general. But looking at the errors actually makes a difference. Okay, so we talked about features which must be numeric. We talked about how to convert discrete features into one-hot features. We talked about sparse and dense representations, all these ones and zeros versus a bunch of random floating point numbers. We talked about bag of word representations and bag of bigrams and bag of trigrams if you've got a really, really, really big bag. We talked about word embeddings, which are really dense representations of the sparse information. They can be pre-trained or trained on the data that you actually have, depending on the distribution. These are things like Word2Vec, GloVe, and the contextualized ones, Elmo and BERT. Then the issue is, are these features enough or not enough? Are you getting the sort of results that you want to get? And are your errors into the random space where you go, I don't know if that's right or wrong? Or you remember, if you're doing reviews, sometimes people say, this is the worst movie I've ever seen, 5 stars. and you think, God, they must be really happy to have gone through life, that everything that they've ever seen in the worst one is still 5 stars. But no, maybe it's a mistake, okay? And you don't know. And so if you're making errors on that, it's not, it doesn't matter, okay? But the question about when you build the actual model, look at the result. You know, does it work? Does it actually work? Could you use it in some actual application that people would pay money for, or whatever the equivalent of pay money for is, use for free so you could spy on them? And when does it fail? When does it not get the answer that it should get? And is that something that's fixable? And what information would be necessary in order to be able to do that? Okay, that's it for today. Are there any questions? Okay, thank you.